Hey everybody, typically I wouldn't combine two concepts here, but these two concepts are really related to each other. There's Dalton's law of partial pressure, and then there's the concept of a mole fraction. Okay, so let's get started here. We have Dalton's law of partial pressure here. Is this going to be, let me not show you the sample problem, but let me go here. So this is Dalton's laws of partial pressure. So that says that the pressure in any container, and I like to think of this maybe a container like a balloon or a bike tire, and I'll talk more about those two things in a second. That says the pressure the pressure in whatever container, excuse me, is equal to the pressure of the individual gases. And so let's say we have a balloon. When we blow up a balloon, we don't blow it up with pure nitrogen or pure oxygen. Okay. A lot of times when we use our mouth to blow up a balloon, we're filling that balloon with air. And we know that air is nitrogen and oxygen and a couple other things. Argon is another thing. So what we can do is, if we want to know what the total pressure is in the balloon, we can add up. We can say that the total pressure, the pressure P, T is for total, is equal to whatever the pressure of nitrogen is, plus the pressure of oxygen, plus the pressure of argon, or whatever happens to be in your mixture. Okay. It turns out that those helium balloons aren't filled with helium completely. There's a little bit of water vapor in them. There's a little bit of carbon dioxide and things like that. And so when we fill it with helium, when we have a helium balloon, what we can do is we can say, hey, it's mainly helium, but there's a little bit of carbon dioxide and a little bit of water vapor. And so that means that the pressure here, the total pressure inside that balloon, is whatever the pressure of helium is, which is going to be close to the total pressure. It's mainly helium. Okay, but there's also the pressure of carbon dioxide and the pressure of water to worry about. So that's what partial pressure is. And now what we can do is we can take, in order to do the mole fraction, what we can do is we can take how many moles of something there is. So again, if we have air that's a combination of nitrogen, oxygen, argon, and other things, okay, if we have air, we can then take the mole fraction. We can calculate how many moles there are and put that over the total moles. So let's say nitrogen, there is 3.5 moles of nitrogen in a sample, but the total sample is equal to 5 moles. Okay, well, the mole fraction is just 3.5 over 5. Okay, now if you want the percent, you would just multiply that then by 100 if you wanted the mole percent. Okay, and then that's going to give you 70%. So that's, or 7. Mole fraction could be 0.7. Okay, so why these are related is because in gases, you don't have to convert to moles. In gases, you can use the pressure, because PV equals nRT. Pressure and the number of moles are related to each other. And so it works out to be the same if you use the pressure instead of the number of moles. Okay, we still are going to call it a mole fraction, but we're going to use the number of moles to, or we're going to use the pressure instead of the number of moles. So here's a partial pressure problem. Okay, in that partial pressure problem, there is 6 grams of O2 and 9 grams of CH4 in a 15-liter container at 0 degrees C. says what's the partial pressure of each gas and what's the total pressure. Well, the partial pressure here, okay, the partial pressure of oxygen is PV equals nRT, but we're going to use, instead of the total number of moles, we're just going to use the number of moles of oxygen. So we have to do some math even before we begin. So we're trying to find P. Do we have V? Yep, 15 liters equals N. We don't have N yet, but remember, N is related to the grams. So we're going to go 6 grams, and we're going to go X line. And remember that oxygen is 32 grams, because it's O2 for every 1 mole. Okay, grams cancel. Let me bring up my my calculator here. And so let's turn this guy on. And so we have 6 divided by 32. And that is so it's 0.1875 moles times R, 0.0821, times T. We have 0 degrees Celsius, so in Kelvin, that's 273 Kelvin. So 273. Okay. So now we're going to take that answer. So now we're going to solve for P. So it's that times, make sure I hit, yep, times 0.0821 times 273. And so we get a pressure of 4.20 atmospheres. And that's the pressure of O2. And so now we repeat that same process, and instead of for oxygen, we repeat it for methane. Okay, so we're going to do PV equals nRT, and this is just for the methane now. So I'll maybe highlight this in red. So we have we're looking for the pressure. The volume is still 15, and now the number of moles is not this, but now we have to do the same conversion that we did up here for oxygen. So we're going to do 9 grams. We're going to convert that from 9 grams. Let's see, 16 grams for every 1 mole. And so 9 divided by 16. And so we get equals 0.5625 times R, 0.0821, times the temperature. I'm running out of room, so I'm just going to continue down here. Okay, great. So we're going to take that. We're going to go times 0.0821 times 273 divided by 15. Did I forget to divide that other one by 15? I think I did. Okay, so I won't go back and do that. So this is equal to 0.840 ATM. Okay, let me come back here. Okay, let me just check my answer just to make sure that, so it's 0.1875 times 0.0821 times 273, and then divided by 15 to solve for P. And so that, thank you for catching that out there, everybody. I'm sure that there were some of you that were going out of your mind trying to figure out why you weren't getting the right answer. And so then that's 0.28 ATM. And so this is of O2. This one here is the pressure of CH4. Great. So that's the partial pressures. But now we want the total pressure. Well, Dalton's law of partial pressure says that if we take these two and add them up, that's the total pressure. So there's the partial pressure of oxygen plus 0.840. And so now we get that the total pressure, P total, equals 1.12 ATM. This plus this. And so that's a partial pressure problem. Now the last one here, okay, so this is where it gets really, let me get rid of the calculator for right now. So we're studying the effects of gases on plant growth. And so we're going to make up an atmosphere, and the atmosphere is 1.5 mole percent CO2, 18 mole percent O2, and 80.5 mole percent argon. So it's mainly a lot of argon. That's crazy, okay? And it says calculate the partial pressure of O2 in the mixture if the total pressure of the atmosphere is 745 torr. So, well, you know what we have to do is we have to convert this to atmospheres. Okay, so that's good. So remember, so this is 745 torr, X line. Every 1 atmosphere is equal to 760 torr. So 745 divided by 760, and so this is equal to 0.980 atmospheres. Okay, but now it gives us, so this is the total pressure. Okay, and it's 1.5% CO2 and 18% O2. Well, so for part A, all we have to do really is take 18% of this number. Even though it's in atmospheres, this number, it's still going to give us a mole percent. We can still use mole percent because they're related as long as you're dealing with gases. If we're not in gases, then you can't do it. But this is all gas law stuff. So there it is. So we're going to go 0.980 atmospheres times, now remember 18%, okay, 18% is really, when we do math, is 0.18. And so let me call up my calculator. You can see the math that I did for that one now. So it's 0.98 times 0.18. And so the mole, the pressure of O2, so the pressure of O2, the partial pressure of O2, is equal to 0.1764 atmospheres. Okay, and it says if this atmosphere is to be held in a 121 liter space, how many moles of O2 are needed? Okay, well, this is the neat stuff. We have a pressure, we have a volume and a temperature, and now we want moles. Well, how do we do all that? Now we use the ideal gas law. PV equals nRT. Well, what's the pressure? 0.1764. What's the volume? 121 equals N, we don't have N, times R, 0.0821. And then temperature is 295. Okay, so now we solve. So it's that times 121. Then we're going to divide in order to isolate N. So we're going to go divided by 0.0821. And then we're going to divide it by 295. And so the number of moles that we need is really just 0.88 moles of O2. So now we're getting into some really good calculations, and we're seeing how all these things can affect each other. Okay, so that is partial pressures and mole percent. And so hope it makes sense. We'll practice this often. See you later.